So obviously, if I'm working with an irregular geometry, I need to get a regular geometry. So in that differential element, I have on each plane. Let's take the plane normal to z axis. Okay, so sorry, normal to y axis. So so this is the y axis, as you can see. Sorry, not normal to y axis, parallel plane that is normal to y axis. Okay, so this one is sigma yy, and one that is parallel to x axis on the same plane, one that is parallel to x axis, we would call it sigma xy. And probably DD sir uses a different notation. Okay, just the reverse, but I prefer this way. The first index is a representation of the direction of the force. Essentially, it's a force per unit area. So the first index is the representation of the force. The second is the representation of the plane on which it is acting. And eventually there is zy. Okay, and you can think of on the three planes you can have total of 9 such components. And obviously in the opposite side you will have the same set of stress components but in the reverse direction. So only on the 3 planes that you get 9 independent components. Actually, even they are not 9 independent components. With laws of conservation of linear angular momentum, it can be shown that the shear components are kind of symmetric, which means sigma xy is sigma yx, and eventually we end up having 6 independent components. And the same thing applies to strain, but it's not through any law of conservation, but that is how we define strain. And we had discussed about this even in our course of finite element method, in brief though. So, but these are all are not the topics that I want to discuss today. So essentially, there are 6 components of stresses and 6 components of strain, and what is the relation between the two? That's what we discussed, even in theory of elasticity. Okay, I mean, you learned about them, not we discussed, but you learned about them. But the thing is, as we discussed today, that obviously what we see as stress and strain are the manifestation. I mean, you apply a given amount of strain in different directions and you get different set of stresses, or you apply different set of stresses and you get different set of strains. Now I'm not going into that debate that the stress is an internal response, what we measure is an external force and all. So all I'm trying to say here is, you apply a given force and you get a given deflection, you get a deflection, and or if you apply a given amount of deflection, you get a given, you need to apply a given amount of force for that. So the relation between the two is essentially the material behavior, and it can be plotted in different planes, like the curve that is shown on the screen. Now these quantities essentially, which are the manifestation of the actual behavior of the material, okay, they result, as we said, from the how the material behaves internally, which means the material which is for us, okay, even in theory of elasticity, you assumed the material to be a continuum. Okay, so have you heard of this term, continuum?
Yes, sir. Yes.
Yes, sir.
Okay. Do you know what that means, continuum?
কোনো ভয়েড থাকবে না ম্যাটেরিয়ালের মধ্যে, ভয়েড স্পেস থাকবে না।
ওকে ওকে ওকে, আমি যেভাবে বুঝি সেটা হচ্ছে যে ইঞ্জিনিয়ারিং মেকানিক্সের একদম প্রথম দিকে যে কোর্সগুলো আমরা করেছি, ক্লাসগুলো আমরা করেছি, মানে আমি বলছি ইউজি ফার্স্ট ইয়ার ইঞ্জিনিয়ারিং মেকানিক্সে, সো দেয়ার ইউড স্টার্ট with particles. And actually, to be frank, Newton's laws are defined for particles. Okay, and the reason they work well Okay, for most of the cases. Okay, unless there is the relativistic effects predicted by Einstein. So it works in most of the cases. Okay. Uh, so of course these particles are not quantum particles. So the particle that essentially doesn't have any dimension. Okay. Now this set of analogy works for real life objects in situations where the object itself is much tiny compared to its surrounding. For example, when earth is going around sun. Okay, if sun is that small, earth is just a dot, just a pick in that space. And that's actually it is. Okay, if you compare the distance between the sun and earth, okay, which is not actually, but uh, can be related to the radius of curvature of the path that earth takes, and compare the size of earth, then you realize that the object itself is very tiny. And in such situations you can approximate an object as a particle. Now a better approximation of a real life object, okay, would be to call it a rigid body, which means we are now considering the object has finite dimension, and along with its translation we are also talking about its rotations, about its own set of axes. Okay, we are saying that the motion of this object now can be described with three independent translations and three independent rotations in 3D. Earlier with the particle model, these are essentially models in physics or engineering. Okay, so that's how we get to solve certain problems very easily. Okay, so they only help us solving the math in a very simple way. So these models, that's what they do. I mean, if you really think about it, the material is composed of molecules and atoms are composed of nucleus and electrons, and that nucleus is composed of neutrons and protons, and those neutrons and protons are composed of even further, you see, uh, mm, some atomic particles, further fundamental particles, and eventually boils down to quarks. Okay, so if you want to look at an object, real life object, okay, let's say if you look at a bridge, okay, and then you can imagine how many of such particles would be there, and just a simple problem of deflection with those many particles would be really complicated for us. Okay, I mean, we'll never be able to solve one. So now a better approximation of real life object is a rigid body. Earlier the object was assumed to have effectively zero dimensions. Now we consider the dimensions, but we also say that the changes in dimension due to the interaction with the surrounding. Okay, that means with the forces that are acting on it are really small, so small that they are negligible, and that's why the material is not deformable. It's a rigid body. Okay. Now, next better approximation is with the deformable bodies, but this time we consider them as continuum. Now, what do we mean by continuum? To understand that, we will have to understand that what is not a continuum. You see, even at the atomic level, I'm not going subatomic. The material is made of crystals and grains. Okay, which means this geometry can be divided into small grains. Now each grain itself can be thought of a larger crystal. I mean, when a stack of crystals arrange in the same fashion, you might be familiar with this. So from your material science courses, so they essentially form a grain, and a single grain itself can be thought of a bigger crystal. Okay, so when these grains, are present, when a geometry is multi-grained, which every material is, okay, unless you have a single crystal or a directionally solidified material, okay. So unless you have directionally solidified, or single crystal geometry. Now the single crystal becomes important with the silicon discs. Okay, which means all the crystals are oriented in the same fashion, and there is just a single crystal all across. Okay, so you need them for certain purposes. Okay, now now if you think about it, when there are two grains side by side, the reason there are two separate grains is because the orientation is one is different from that in the other. The orientation of the atoms is a if they are different, then they are two separate grains. And obviously the grains have grain boundaries. Okay. Now, even if we assume that the grains as a single, as a unit quantity, okay, then let's say if I draw a line across the geometry, okay, and let's say the coordinate along that line is s, and if I'm trying to plot any property, let's for the sake of simplicity assume a scalar one, which is a density. Okay, now wherever there is a grain, there will be certain variation, but because the grains are in different orientation, they are bound to have something called the grain boundary. Okay, so I'm not even going into the details of the what type of void, what type of dislocation, what type of point defect or line defect that are there. I'm just not going to that. But if there are different grains, okay, there would be grain boundary, and at the grain boundary, what happens to this quantity? It just ceases to exist, right? So if once you proceed in the second grain, there is that quantity. So essentially what happens is the curve that I'm trying to plot here is not continuous. And now if you think about it, if the grain size is much smaller compared to the geometry itself, so this curve essentially doesn't look like this. It doesn't look like that exaggerated. It just looks like a series of disconnected line segment, which can effectively be thought of a single line. Okay, single continuous line. And that gives us the approximation of continuum, which basically means, yes, we accept that the material has pores and holes in them, and there are discontinuities, there are grain boundaries, there are so many things, okay, but they are just so much tinier, okay, that effectively we can think of that the properties are changing continuously within the material. Not just the properties, any quantity. If the temperature has to change, that would also change from one point to the other continuously. Okay, and that only gives us the ability to do all sorts of differentiation. And if you have learned anything from finite element method, that is to solve everyday problems in physics, we need to be able to solve differential equations. Okay, and that requires two things. One is that you are good at solving differential equations, and number two, that the everyday object, when they are behaving in different way, okay, electromagnetic way or in a mechanical way, whatever way they are interacting, okay, you should be able to pose a differential equation, partial differential equation or ordinary differential equation. Okay, and the only way you can pose a differential equation is when you assume the geometry to be a continuum. এই অবধি বোঝা গেল?
হ্যাঁ স্যার।
Okay.
এই লাইনটা কি লিনিয়ার হবে?
মানে তুমি বলছো স্ট্রেট লাইন হবে কিনা?
হ্যাঁ, এক্স্যাক্টলি।
জানি না, হতেও পারে নাও হতে পারে, কি যায় আসে, আমি জেনারেল আনছি। আমি কিছু অ্যাজিউম করছি না। ইনফ্যাক্ট ডেন্সিটি কনস্ট্যান্টও হতে পারে, মেটেরিয়ালটা হোমোজিনিয়াসও হতে পারে।
আচ্ছা
ঠিক আছে, তো যেটা বলার যে এই যে দুটো সাবজেক্ট, whether it is theory of elasticity or theory of plasticity, okay, it's not the most ground level subject. Okay, it's not the subject. I mean, it would have been great, okay, and I would like it to be able to discuss few of the things about the microstructure, and of course we will probably discuss in brief, okay, about microstructure, but the course is predominantly about the macroscopic behavior. It's not uh, looking at the elasticity or plasticity from the microscopic sense. It is looking at that behavior from the macroscopic point of view, which basically means that our models are more crude. Obviously all we will be doing is, learning a set of models, okay, and those models have been established by checking over and over with the actual material behavior. Okay, in case of plasticity, with a lot and lot of ductile metals, okay, they have been verified, those models. Okay, and if one model doesn't work, you go for another. But the thing is, those models, I mean, they are not random. Okay, they have been benchmarked, they have been verified. Okay, uh, having said that, but we would be restricting ourselves to models. Okay, all of these are models, even what you see in the microscopic level. Okay, when you try to model atoms as hard spheres, okay, you must have heard this term, hard spheres. Okay, but atoms are not spheres, let alone being hard. Okay, so even that is a model, and there is no stopping this. It's just the models improve, but the models exist. Okay, I mean, nature created everything. Okay, uh, but your understanding, okay, is a layer upon layer improvement of the models. Okay, and whatever is being done, even in the fields of quantum mechanics, is to improve our models. Okay, so and that also is true for everything related to relativity. But we are here doing very uh, um, very Newtonian mechanics. Okay, very simple, totally Newtonian in mechanics. Even in that, you need to understand that the model still improves from here. Even though we would be restricting ourselves to continuum model, okay, but we need to know a little bit about the microstructure as well. So that probably we would do in the next class. Um, but about this course also, again, regarding the continuum model. So, so whether it is elasticity or plasticity, okay. So at first we look at different set of models, okay, and then we try to establish a framework to solve different problems with that set of models. Okay. So that's what we would be trying to do. We being engineers, our goal is to solve engineering problems. Okay, and how we can implement such models in engineering problems is essentially what we would be end up doing during this entire course. Okay, so so although the title is theory of elasticity or theory of plasticity, but those are what we are doing over here is only studying the utility of the models of either elasticity or plasticity. Okay, because if you really think about it, elasticity or plasticity are essentially the manifestation of the microscopic behavior of the material, and in either of these courses we would be only briefly touching about such microscopic behaviors. In the theory of elasticity, did you look into any microscopic behavior of the material?
No, sir.
No. Here we'll be doing in brief, but eventually we'll realize that that is actually not not an essential part of the flow of this course. Okay, even if you look at the book itself, the discussion on the microstructure, that is a separate portion. Okay, I mean, it's one of the initial chapters, but it has nothing to do with the rest of the book. Okay, that's how the subject is, unfortunately. Okay, so for example, if you have studied how the torsional, what happens with the torsion, okay, what set of stresses do you get within the geometry? Okay, you have done that in way past in your undergrads in strength of materials, but you have also done it possibly in theory of elasticity. We would also study torsion with plasticity involved. Okay, and again, since we are talking about improving our model, you already know this, right? That the type of elasticity that you studied is linear, and linear elasticity is a property of the metals. Only metals show linear elasticity. I hope you understand. Recognize this modulus over here. It's the Young's modulus, and that is only true for this much amount of strain. Okay. Actually, even smaller, not more than this much amount of strain. The metal is no longer elastic beyond this much amount of strain, and beyond this point, the material is plastic. Okay. Now, what makes plastics plastic is, can you tell me what happens if I try to unload the material at a certain load? That means I want to remove the entire stress. How would the curve look like? So this is the loading curve. We always draw the loading curve. Okay, but what would happen if I unload, let's say from point P over there?
Sir, some permanent deformation remains, and the curve goes back to the strain axis, but there is some permanent deformation that is remained.
But how much permanent deformation? By simply looking at the stress value.
প্যারালালি ওই লাইনটার নিচে নামবে।
So yes, you are correct. So the unloading is always elastic. Okay, and that creates the problem. Okay, you see, what we do not consider is even beyond the yield stress, and I'm just casually saying that the yield stress is your proportional limit and yield stress is your elastic limit. Okay, which is not the case, but let's say that's what it is. Okay, so beyond that stress, okay, we know that the plastic deformation is happening. Essentially, that's what yield stress means. But that doesn't mean no further elastic deformation is happening. Okay, elastic deformation always happens every time there is a change in stress, and the change in stress is only due to elastic strain. If there are only plastic strain, there would be no change in stress. You must have seen this curve called elastic perfectly plastic. Being perfectly plastic means when it starts deforming in plasticity, there is no further elastic deformation is happening. Okay, so how much would be the elastic strain once you reach point P? Let's say delta sigma is your rise in stress, so delta epsilon elastic would be simply delta sigma by E, which basically means this much strain. Okay, so this is the slope E over 1. Okay, this is the slope E over 1. So this much is the strain caused by, there is a sigma rise in, stress. That is the elastic strain. Okay, and rest of what has happened, beyond this value, beyond elastic limit, a total of this much strain has happened. But out of that, this much is elastic. And when you unload whatever has been elastic. That means you unload this portion that happened before having plastic deformation and this additional portion. That means a total of this much is unloaded, which is, this value is sigma at P divided by E. Okay. And if the total strain at P is epsilon, okay, I shouldn't be calling it epsilon P. So epsilon P is the plastic strain, and that is this total strain minus whatever is elastic, because that is the part which could not be recovered. Okay. Again, all of this is a model. All of this is a model that simplifies the math. To be frank, this is not exactly how material behaves. Okay. It behaves very close to that, but this is not exactly how it behaves. For example, when you unload, the slope is exactly not the same, first of all. And when it reloads, it goes slightly left. And what is supposed to happen is, it is also supposed to, yield from the stress from which it has been unloaded. But that's not exactly happens. Okay. It follows a slightly different curve. Okay, on reloading. So there is loading, there is unloading and reloading. Okay, they are very different curves. Those are the actual material behavior. That is how the nature has created the material. And to be exactly able to model that, we need better models. We need models that are based on the microscopic behavior. Okay, more and more depth into that would enable us to exactly model that stress strain curve right there. Okay, but us being engineers, even that approximate behavior works in most cases, and therefore we can stick to a model which basically assumes whatever we just discussed. Okay. Okay, so so now to the topic that why plasticity is a better model. Okay, now when we talked about particle, rigid body, then continuum, then the microscopic models. Okay, and even further, we were looking at the behavior of the material. Okay. Or the material's ability to, looking at the structure of the material. Okay, that gave us the depth of the structure of the material. But this time I'm talking about how that structure behaves, how that material behaves. Okay, that entire course of elasticity that you studied, that only applies to the tiny portion of the strain. A ductile material can have 20% of strain or 30% of strain. That is 2 orders higher, that much of strain before having a fracture. Okay, and you are 200 times below that strain. Okay, and whatever you have learned in the previous semester only applies to that 1/200 of what the material can actually do. the total amount of deformation that the material can actually have up to the point of fracture. If we are talking about a ductile material, okay, a typical ductile material. Now, that might make you feel small, but let's think about it. Most of our designs, okay, are within elastic limit, okay, and it's not that we design based on sigma y. We divide sigma y with a factor of safety, and if it is a brittle material, we use the sigma ultimate and divide with the factor of safety, which is actually higher than the factor of safety for ductile materials, much higher. If this factor of safety is of the order of 2.5, this probably would be, around 10. Okay, and that only gives us the working stress, and we try to keep the highest stress below that stress. Okay, are we over designing? Yes, in some cases we do. But let's think about it. All of those design problems that you did in your strength of materials and all, okay, most of them were based on static loading. And material is often subjected to dynamic loading, like fatigue loading. Okay, and you know already this, that the material fails much faster with fatigue loading. Do you recall Soderberg equation and all related to fatigue?
Yes, sir.
Yes, sir.
Okay, so go visit that chapter. You probably studied that in one of your design courses. Go visit that chapter. Okay, and you will realize what I'm talking about. Okay, so essentially you have the sigma y on the x-axis for the static load, and for the dynamic part you have the sigma e, and let's say sigma max is the maximum stress in your cycle, and sigma mean is your the minimum stress. Then you calculate the sigma average as your what is called, sorry, average, that is sigma max plus sigma mean divided by 2, and then you take sigma v, the variable part is sigma max minus sigma mean divided by 2, and then you do is what you do is you take one of the axes as sigma a, the other one being sigma v. Okay, and the simplest model is essentially a straight line. Okay, where if there is no variable load, that means the sigma max and sigma mean is the same, then what you do is then the maximum stress that you can allow is sigma yield divided by some factor of safety. And if there is no the non-zero, if the average is 0, if there is only a variable load going from minus sigma max to minus sigma max, plus sigma max, then you have the endurance strength, okay, divided by the factor of safety. Okay, and I don't recall if that one is Soderberg equation or not, but one of the equations, whether the linear approximation or the quadratic approximation, is Soderberg equation. Now, obviously, if we are working with brittle material, we'll have to change to ultimate stress and a different factor of safety. So, so you see, that is how we design. Okay, even today, in most of the cases. Okay. So, having said that, it means that all our designs are well within the elastic limit, and the failures might happen even within the elastic limit when there is a fatigue load. So the point is that the very fact that the elasticity is only there up to 1/1000 of strain, okay, that doesn't mean that the theory of elasticity finds a very little approximation, little application, okay, only in 1 in 1000 cases. That's not the situation. Okay, you need theory of elasticity for most of the design works. But you see, the thing is, ductile materials can take little bit of plastic deformation. Okay, and they could be going through a fatigue cycle with plastic deformation. Okay, maybe a very tiny amount of strain, but they can have that much of strain, plastic strain. Okay, and sometimes having that much of plastic strain is not avoidable. Okay, but if you want to study those, how do you study? That is beyond the scope of theory of elasticity, and that's why you need to, you know, uh, enlarge the boundaries of your understanding and incorporate theory of plasticity into it. Okay, so today being the introductory class, that is where I want to stop, and I will, ask you to ask me if you have any questions.
So in production, we have that metal forming and curve drawing that also comes under plasticity.
That also comes under plasticity. Yes. Yes, that is a good point. That yes, you see, although we restrict ourselves to only uh, designing component within elastic limits, but how do we create those components? That is through plastic deformation, and even the material might fail while we are, trying to create those, or maybe we want to design a mechanism that creates a certain geometry. So we need to know how much force should we be applying, and again, for that we need to have the understanding of theory of plasticity. Okay, and again, we are not discussing about the microstructure behavior here. We are only discussing the macroscopic behavior. We would be using continuum mechanics and so on, but still that finds its application in these topics we just discussed. Okay. Okay, so we'll meet on next Wednesday.
Okay, sir.